Thank you so much, and thanks everyone for coming. Thrilled to be here. So I'm going to talk to you today about a recent result we have on new algorithms for the Earth mover distance. In particular, this new hash family for the Earth mover distance. This is called locality-sensitive hashing. If you haven't seen it before, we'll go into it, so don't worry at all. So this is a joint work with my co-authors, Eric Weigard and Tian Zhang, who's a student at UPenn. So we've been working on these fast, high-dimensional geometry problems for Earth mover distance and similar things for a while now. So excited to tell you about this result. So let me start probably by telling you about what Earth mover distance is. So if you haven't seen it before, Earth mover distance, I like to think of it as like a meta metric. It's a metric over another metric space. So if you have some base metric space X, Earth mover distance is a metric over subsets of that metric space. So if I give you two subsets, A and B, let's say they both have exactly S points and they're subsets of X. The Earth mover distance between A and B is the cost of a minimum perfect bipartite matching between the points in A and the points in B. So you go through, you try to find the best possible matching between the points in A and the points in B, and the cost of that matching is the distances in the underlying metric space. So it's kind of like perfect bipartite matching with a triangle inequality, because the edge weights are exactly the distances in the underlying metric space. And let me just say that right now we're going to assume for the rest of the talk that all the sets have the same exact size, S, but it's very easy via some standard duplication and smoothness to like have different size sets. So they don't actually need to be the same size, but it'll be way simpler for the talk to think of all sets having exactly the same size. So you have your two sets and you want to find the best matching between them, and the weight, the sum of the edge weights of the smallest matching is the Earth mover distance. And I should mention, feel free to interrupt at any time for questions. Hopefully this shouldn't run over, but yeah, so please feel free to interrupt. So this is an object. Why do we study this metric? It's a little more complicated than most metrics. Well, it's a natural metric over sets of objects. And this actually ends up being very important for a lot of areas of computer science. One of them is in natural language processing. So this is sort of a classic approach, classic being 8 years old now, and that's classic for NLP. This goes after a paper of Kusner, Sloan-Kolkin, and Weinberger in ICML in 2015. And this had this idea of using Earth mover distance to look at document similarity. So if I have two sentences, Obama speaks to the press in Chicago, and in Illinois, is the president agree with the media? These sentences are basically saying the same thing, but they have no words in common. So very classic methods of NLP, which look at bag of words, would say these sentences are dissimilar. But you can see there's a very natural matching between the words in these sentences. Obama is the same as president at the time, speaks is like greeted, Chicago is in Illinois. So there's sort of a natural semantic matching. And the way we can make that a nice computer science problem is we can use word embeddings, which take each one of these words and embed them into a high dimensional Euclidean space, such that similar words map to similar vectors in the metric space. And now I could just use Earth mover distance on these word embeddings, this set of vectors, as a proxy for the similarity between these words, these sentences. So you can see that Obama would map to a similar vector as president, media maps to a similar vector as press, and so on. And so a small Earth mover distance between these sets of vectors indicates that these sentences have similar semantic meaning. And this was used quite a lot. This was a very popular paper. And now I want to mention very briefly that there's sort of a even more modern take on this, and this is called contextualized embeddings. So what we do today, and this is extremely common, is we, instead of embedding each word independently, we take the entire document and we send it through a so-called self-attention model. All this means, from the purposes of theory, is that all the words, when they're getting an embedding, attend to each other, which means that their embedding depends on the rest of the context, the rest of the words. So the embedding of bike doesn't just depend on the word bike, it depends on all the words that came in the sentence with it. So this is giving a way richer embedding of the words. The only reason I bring this up is that this is actually using these embeddings for information retrieval, document similarity, is the state-of-the-art method for a lot of large tasks, NLP tasks. So if you look at the BEAR benchmark, which is the standard benchmark that people use to look at information retrieval tasks along with clustering and a lot of other NLP tasks, these methods based on multiple vectors and this kind of similarity give state-of-the-art results. So this is quite a powerful technique to use. And so what is this information retrieval task that I'm talking about? And this is going to sort of segue into the main problem, the main theory problem of the paper. Well, you have some data set, think about all the pages on Wikipedia, and you're going to get some query, like when was Abraham Lincoln born? And your goal is to pre-process this data set. So given the query, you can very efficiently find the documents that were relevant to your query for like question answering or retrieval augmented generation or any of the modern ML problems you want to solve. So of course you would want to retrieve the Abraham Lincoln Wikipedia page for this. But you really want to do this with query time way faster than a linear scan through the data set. You don't want to look at each individual data set, look at the similarity, and find the most similar one. That's not efficient. So we want to do this very quickly. And in theory, this problem is called nearest neighbor search. And this is, a problem that like has sort of a literature of its own in the last 30 years. And it's all based on this following sort of 3-line formalization. The nearest, and we're going to deal with the approximate nearest neighbor search problem because we want to allow ourselves for faster algorithms. So here's the problem. We're going to have a metric space, and we're going to allow some approximation factor C larger than 1. And our goal is to pre-process this data set, a subset of the metric space with endpoints, such that given a query from our data set, we can very quickly find a C approximate nearest neighbor from the data set. Whereas C approximate nearest neighbor is just any point that's within a factor of C of the closest point to our query. So if Q is the query and Y is the closest neighbor at distance 1, I can return any neighbor within a ball of radius C, but nothing further. So this is a classic problem. It's been studied for many different metrics. It's dating back to the mid-90s, where a lot of work was done on it. I want to mention really briefly that it's important to note that EMD, to remember for the talk, the EMD is a metric over sets of points. So what this looks like for EMD is every point in the EMD metric space is a set of points. So like the squares are one point in EMD, the triangles are one point of point, and your query is a set of points. And you want to find the data set point which has the smallest EMD to your input set. So just keep in mind that when I say a point in EMD metric, I'm talking about a set of points of size S from some ground truth metric. It's easy to get that confused. It happens to me all the time. OK, so before we go further, I have to do a bit of boring housekeeping. So I'm just going to have this notation here, this EMDX dx. This is going to be the notation for the metric space of S points subsets of X under the EMD metric. And for the rest of the talk, X is just going to be a d-dimensional space under the L1 metric. The reason we use L1 is that it's more general than L2. You can embed L2 into L1, and you can embed lots of other fun metrics into L1. So L1 will be a good metric to use as your base metric. I'm also going to assume that all my distances between the points are between 0 and delta. That's going to be the aspect ratio. And we can actually assume the dimension and delta are some polynomial in S. There's an easy reduction to that case, but it's not important to mention here. So just to recall, D is the data set we're going to have that we want to pre-process and get very fast query answering from. N is the size of that data set, and S is the size of one of the multi-sets of my EMD metric. And let's think of N as being much larger than S, because N is like the number of points in my data set. S is just the description size of a single point. So N is going to be larger than S. OK, now that we're done with that, we can move on to what we can sort of hope to get. So here's a classic result, which I'm going to call like the gold standard for nearest neighbor search. This is kind of the best kind of guarantees we could hope to get. And this dates back to a paper of Indik Matwani from Stock 98. And what the trade-off they got is if you fix an epsilon, this is going to be related to your approximation. They get an approximation factor of 1/epsilon with pre-processing time that's nearly linear, n to the 1 plus epsilon, and query time that's very sublinear, n to the epsilon. So much faster than looking through every single document. So, and this is for the L1 metric. And this is actually optimal for L1, meaning you really can't get much better trade-offs than this. I won't say exactly how the lower bound works. It's conditional on like certain models, but more or less this is sort of the best you could hope for L1 and for a lot of other metrics. You can do a little bit better for L2, but let's not really worry about that. And if we want to just sort of simplify the trade-off, we can sort of forget about the space and pre-processing time and just look at the trade-off between approximation and query time, n to the epsilon, and then 1/epsilon approximation. That's sort of the core trade-off that you could sort of hope for as a gold standard. So this is actually, quite good if you think about, in like square root n time, you can get a 2 approximation roughly. That's kind of surprising. Even in high dimensional space, there's no dependency on D here in the approximation. And how do these results come about? Well, they come from this technique called locality sensitive hashing, which is the title of the talk today. And this technique is sort of one of the most powerful ways of solving nearest neighbor search problems. And it's actually a quite simple idea. It's a hash function that is applied to a metric space that has the property that similar points under the metric space are more likely to collide under the hash function. So it's not a random hash function. It respects the geometry of the underlying metric space. So formally, I've defined it in a way a little bit differently than some papers, but this is just to make it a little bit easier to parse. I'm going to set a value epsilon and a threshold r. R is just the threshold in the metric space. We're going to say that an epsilon r CR LSH family, it's a hash family with the property that for any 2 points in my metric space, if they're close, if their distance is less than r, the probability that they collide is large. It's greater than 1 minus epsilon. On the other hand, if they're far, if their distance is larger than c times r, the probability they collide is small. It's less than 1/10. So this is just the definition, and the smaller epsilon is, the bigger the gap between close points colliding and far points colliding is. And just to see very briefly how you could use this for a nearest neighbor search, imagine I set epsilon to be 1 over 100 log n. And remember, n is the number of points in my data set. Then what happens, let's now take g of x to be a k-wise concatenation of my hash function. So I'm just going to take k of them and concatenate them together. Then to collide under g, you have to collide k times under h. So these collision probabilities get raised to the power of k, and k is like 10 log n. So what does that mean? Just a simple calculation is now that the probability that 2 close points collide is at least 2/3, but the probability that 2 far points collide is way smaller. It's like 1 over n squared. So now you could union bound over all the far points. And so given a query, you'll never collide with a far point, and with probability at least 2/3, you collide with a close point. So now you have a very simple algorithm for nearest neighbor search, right? You just draw one of these hash functions, build your hash table in preprocessing, and when you get your query, just query your query, look at the hash bucket, and see what it collide with, return any one of those points, and you're guaranteed with probably 2/3 to have found a close point. So that's a very simple algorithm if you had such a LSH for nearest neighbor search. So there's a very easy reduction from LSH to nearest neighbor search. It turns out you can have a more general result than this. For any epsilon, and this is a generic reduction, if I give you one of these LSHs, epsilon RCR, you can get a nearest neighbor search algorithm with n to the epsilon query time. And the approximation is 1 over epsilon. So it's quite a general, well, I guess it's a C approximation. Sorry. You get a C approximation, which is whatever C comes from the LSH, and then runtime is n to the epsilon. But for whatever LSH family you'll have, the C will probably depend on epsilon. So this is just the definition. By now we have a really good understanding. This is like a almost 25-year-old definition. We have a really good understanding of these things for all the basic metric spaces that you see a lot of, like L1 distance, Hamming norms, L2, Jacquard distance. But that's not the case for EMD. We don't really have a great understanding of like the tight bounds for what you can get for LSH for EMD. And it's kind of not surprising. EMD is a much more complicated than metric than L1 or anything like that. And in particular, what I mean by complex here is like EMD doesn't decompose into a sum of distances over coordinates like L1 does. It's like some complicated min-cost geometric bipartite matching problem. And just to give you an idea, like if you wanted to solve this more than, let's say, 10 years ago, you would use the Hungarian algorithm, which is over a 100-year-old algorithm, dates back to Jacobi in the 1850s. We could do it a little bit faster now using fast min-cost flow solvers, but it's strongly believed under like Seth that you can't do any better than quadratic time. So this is a computationally hard problem compared to like linear time distance computations. So it's not so simple. But what was known? Well, there's a couple of results known. The first one, I think, dates back to Indyk and Stockov 2004. And what Piotr showed was that you can get a nearest neighbor search data structure under this Earth mover distance metric, with the ground set being L1. And you're going to get a sort of similar looking trade-off as we saw for L1, with the addition of this sort of painful term here, this d log s. So it's the same approximation query time trade-off with an additional d log s approximation in the approximation factor. Remember, d is the dimension and s is the number of points. So this is not ideal, especially if the dimensionality is large, if we're in high dimensional space. So this was improved in SOTA 2008, Andoni, Indyk, and Krauthammer. They were able to go from d log s approximation to a log squared s approximation. So for high dimensional space, this is an improvement in the approximation factor. And the query time in space is all the same. It's n to the epsilon, n to the 1 plus epsilon. So this was an improvement. And the main thing I want to tell you about today is a further improvement. We get roughly a quadratic factor improvement in here. We go from log squared s to tilde of log s. So that's the main result of this paper, is that you can get a nearest neighbor search data structure and n to the epsilon query time with 1 over epsilon log s approximation. And so this is the result I'm going to tell you about. But really, the result is about space partitions in LSH. And in fact, these two papers, the first two, weren't even talking about nearest neighbor search. They were more about sketching in LSH. So let me rephrase what these papers actually sort of showed. These papers were sort of telling you about the existence of certain families of localities of hash functions. In fact, they didn't mention nearest neighbor search anywhere in the paper, although surely they were, these guys are big nearest neighbor search folks. They know about the problem. So Piotr's paper can be phrased as the existence of a epsilon r d log s LSH. And the paper of Anindya, Indyk, and Krauthammer can be phrased as an epsilon r log squared s LSH. Now, the reason I put it this way is that under this language, the main result of that I want to tell you about today can be phrased as a epsilon r tilde log s data dependent LSH for Earth mover distance. So the first two results were data independent. What we prove is the existence of a data dependent LSH. Now, I haven't told you what that is yet. We'll do it on the next slide. But this shows you that the improvement isn't exactly the same apples to apples kind of result that they got before. We gave a slightly different kind of hash function. So what is this contraption? What is a data dependent LSH? Well, it's a very similar definition. First of all, one property to note is that the hash family is allowed to depend on a data set D that's given as input. That sort of makes sense. It's called data dependent. So you look at the data set D, and you can construct your hash family as a function of D. Now, what are the guarantees? Well, the first guarantee is exactly the same. For any 2 points in your metric space, close points should collide with a good probability. But the weakening is that for points that are far, for any point x in my metric space, think of as a query point, I only need to split from far points that are drawn from my data set on average. So I have a query point x, and I only need to split from far points on average over a random draw z from my data set, such that z was actually conditioned on being far away from x. And this seems like this is a weaker condition, but it turns out that it gives you it's just enough it gives you the same reduction to nearest neighbor search. If I gave you one of these contraptions, you can get the same reduction to nearest neighbor search with an n to the epsilon query time and a C approximation. So if we're just worried about nearest neighbor search, this is just as powerful as data independent LSH. But we have a lot more power in designing the algorithm because we can mold the data set is still worst case, but we can mold our hash family to the data set and exploit structure of that data set, and that's what we're going to try to do. Any questions about LSH or the definitions? Cool. So before I jump into go ahead. Yeah. I mean, this is also going to have nearly linear n to the 1 plus epsilon preprocessing time. So the thing, I don't want to focus so much on preprocessing time in space, but there's things you could do like exponentially. You can compute the Voronoi diagram of your space. But I want to eliminate things that do exponential in dimension. Like as long as you're polynomial in n, there's nothing too tricky you can do. But in fact, we're going to be better than we're going to be nearly linear in n. But yeah, usually what I would say in an LSH talk is that we don't want to allow things that are exponential in the dimension, because you can do like epsilon net times arguments where you pre-compute all nearest queries and stuff like that. Also note that would be very expensive because for Earth mover distance, the doubling dimension is not d, it's sd, because there's s points in d-dimensional space. So it's like 2 to the sd possible points roughly. So we want to be polynomial in s and d. So before we jump into like the actual meat of what's going on, let me just sort of give you a bird's eye view of how this result comes about. And it comes about really by focusing on these things called tree embeddings. So it turns out that all the prior work on EMD, even in sketching and streaming algorithms for the most part, but also in nearest neighbor search, the results come from these things called probabilistic tree embeddings, in particular fast tree embeddings that are very quick to compute. There's an older literature on tree embeddings from papers like Bartal and FRT. These won't be useful for us because they're not as quick to compute. I just mentioned that for those of you aware of it. We won't need to think about them in this talk. So there's these two results that I want to talk about for tree embeddings. The first one is this paper of Anindya and Krauthammer that we just talked about. And really what that paper showed was a log, I said it again, they didn't even talk about LSH in that paper, but really what they showed is a log squared S approximation for a tree embedding of space. Again, I haven't told you what a tree embedding is yet, but we'll get there. So a couple of years ago in Stock, we were able to actually improve this result with my co-authors Shi Chen, Amit Levy, and Eric Weingarten. We were able to show an improvement in the approximation of so-called tree embeddings to log of the size of the data set. So we gave a data-dependent tree embedding. It doesn't embed all of the space into a tree. It just embeds a fixed data set. And the approximation is log of the size of the data set. So this is our starting point. But we can't use this result because the data set here has n points in it. So we would get like a log n approximation. Also, our query isn't in the data set, so we don't know how to map that yet. There's some issue with that. But what we're going to do is we're going to use that as a starting point, and we're going to sample poly S points from that data set, from the data set we have as input. And we're going to run that data-dependent tree embedding on the sample. So now we have a good approximation for the points in the sample. And then sort of the key technical step that we're going to get to is we're going to do a so-called neighborhood extension. We're going to extend that mapping from the sample to the tree to all of RD to the tree. So now it's going to be a legitimate mapping of all the points into a tree. And we're going to lose something, but it's still going to be a good approximation for points that were close to the sample. We sampled some random points. We had a tree embedding on them, and we extended it to all points. And for points that were near the sample, it'll be a good approximation. And then sort of the way we're going to finish this up is that we're going to say, what do we do for the points that are very far, like log 10 far from the neighborhood of the sample? Well, we're going to go back to that other embedding, which is a worse approximation. It was a log squared S approximation. But that's good enough to distinguish like R from log to the 10R. So that's going to, this log squared S approximation is going to be enough to handle the far points. It's going to be able to split away the ones that weren't in the neighborhood. So we're going to glue these two things together, handling things that are close to the sample with the data-dependent embedding, handling things that are far from the sample with the prior data-independent. So this is the roadmap for the talk. Okay, so I should probably tell you what a tree embedding is. So let me start with that. So probabilistic tree embeddings have a long history in the computer science, and I'm going to talk about a very small class of them, these fast tree embeddings. But essentially, the idea is to take a complex metric space and to embed it into a much simpler metric space. And trees are very simple metric spaces. So as we mentioned, Earth mover distance is not a simple metric. But it turns out that Earth mover distance, if your base metric is a tree metric, actually is quite a simple metric. And the reason for that is that if my points were in a tree metric, it turns out that the greedy matching is optimal. And what I mean by the greedy matching is you look at your points are some vertices in a tree, and the distance is the shortest path metric on the tree. And if I just like greedily push my points together and match the closest ones together, and every time they're in the same node, I match them together, sort of a greedy bottom-up matching, this matching is guaranteed to be optimal. And it doesn't matter how I match them up in the node, it's arbitrary. So the greedy matching is optimal for when you're in a tree metric. The only reason that's important is that this allows you to actually show that EMD over tree can be embedded into L1 with no distortion. I won't give the reduction, but it's a fun problem. You could probably do it in a couple of minutes if you try to work it out. But what I mean by a metric embedding here is that if I have two sets of points, Earth mover distance over a tree, I can embed a set of points into a single vector in L1, such that the distance between those vectors in L1 is exactly the Earth mover distance in the tree. So Earth mover distance in the tree is just as easy as L1. It's the same metric. It's contained in L1. So that means that we can always just use nearest neighbor search for L1 to get those trade-offs once we're in a tree with no additional distortion because this embedding is isometric. So the task is going to be, how do we get into a tree? How do we embed Earth mover distance over high dimensional Euclidean space into Earth mover distance over a tree? And we want small distortion because that's going to be the main cause of distortion. So first, let me tell you about this first embedding, which I'm going to call the quad tree embedding. This is the embedding from the Andoni, Indic, and Kraft-Gammon paper. So what is even the general idea of how you do such an embedding? Well, it's fairly straightforward. I'm going to take my d-dimensional Euclidean space, and I'm going to randomly or recursively subdivide it. Every time I'm going to divide space up, and then I'm going to recursively subdivide it. This creates a recursion tree where each space, every vertex corresponds to like a hypercube. And then I divide it, and the children of that point are the subdivisions of that hypercube. So I'm going to recursively divide. Yeah. Well, you can do it. You do it at one. Like on the next slide, it'll be more formal. But it's going to be like a random hypergrid. You take a hypergrid, and then you randomly shift it. And then you do that recursively for smaller hypergrids. And that's the full embedding. So vertices of the tree correspond to subsets of the points in RD. They actually correspond to hypercubes. And what is the mapping? I take a point in my space, and I map it to the leaf of the tree, where that leaf just corresponds to that point. If you subdivide enough, you just get a single point. And then to make this a bona fide tree metric, we need to set edge weights. So what we're going to do is we're going to set weights of the edges of this tree in a way so that the distances in the tree should approximate the original distances, because that's what we wanted anyway, right? So that's going to be our goal. And because we're dividing at geometric intervals, it turns out, as you guessed, the edge weights are geometrically decreasing as you go down the tree. So what that means is that really the distance between 2 points is decided by the first node where they split in the tree up to a constant factor. So the picture is you have your points, let's say on the plane. I'm going to, just for the sake of simplicity, make one cut, splitting them randomly in half. That creates 2 children. Then I'm going to make another cut, and I'm going to keep doing this till all the children are in their own vertex at the bottom, and that's the mapping. This point goes to that point in the tree. So this is the tree embedding. A bit more formally, like I mentioned, the actual algorithm is going to impose a randomly shifted hypergrid at log d delta scales. At each time, you cut the side length in half, and you shift it again, and this gives a random recursive partition of space. We're going to let T be a recursion tree, and a vertex in that tree, let's say V, we're going to let S sub V denote the hypercube, the subset of space corresponding to that vertex. And what we're going to do is for any vertex U and V, we're going to set the weight of the edge between them to be d delta over 2 to the I. Now, it's not exactly important what this weight is, and you can feel free to forget about it after this slide. But what it is important is that the weight of this edge doesn't depend on the data set you're embedding. It's a fixed weight. It just depends on the depth. So if the edge is at depth I, it's some d delta over 2 to the I. So in particular, the metric itself doesn't depend on the points that you put into it. Of course, we'll see in a moment that that won't be the case for some future embeddings. And then, of course, the function is just mapping a point A to the leaf containing it. This is a mapping of RD to a tree. But this naturally induces an embedding from earth mover distance over RD to earth mover distance over a tree, just by embedding all of your points, your S points in RD, into your S points in a tree. So now we have an embedding of earth mover distance over RD into earth mover distance over a tree. And what is the question we want to ask? Well, we'd like to know what was the distortion of this embedding. So what Andoni, Indyk, and Krauthammer were able to prove is the following kind of statement. And this is the kind of statement that's very typical of these probabilistic tree embeddings. So first, they show that the distances are non-contracting with good probability. So for any 2 points, individual vectors in d-dimensional space, their distance in the tree is at least their original distance with probability 1 minus 1 over poly S. S is, you get to choose S in this case. And moreover, they don't expand too much in expectation. For any 2 points, their distance expands by most a log squared S factor in expectation. It turns out that this is enough to embed EMD. Why is that? Well, first of all, note that expected expansion is enough for EMD, because I only need one matching to not increase in cost too much. In particular, I only need the optimal matching to not increase in cost too much. So in expectation, that matching doesn't increase in cost too much. For all the other matchings, I need them to not decrease in cost too much. But there's only, if I have S points in each of them, there's only S squared pairs. I can union bound the contraction statement over all of them to show that they don't shrink by much. So this statement alone is enough to show that the earth mover distance between 2 points embeds into the tree metric with a log squared S distortion. And you may ask, what about the n other points? Do you need to union bound over n points? It turns out you don't. I won't say why, but you could sort of embed into, because you have an expected bound, you can embed sort of into a collection of trees and get basically the actual distortion will end up being the expected distortion. Is this part what? This part is not data dependent. So far, all I've done is describe the embedding of Andoni, Indyk, and Krauthammer from 2008. So this is how they get the log squared S approximation for EMD. So now I'll tell you about the data dependent part. So that's what I'm going to call the data dependent quad tree embedding. And so this was a paper of myself and a couple co-authors, Shi Chen, Amit Levy, and Eric Weingarten. And what we did was we made a very small modification to this algorithm. We just changed how the edge weights were set. So we used the same exact recursion tree and the same exact space partition, but we set the edge weights in a data-dependent way. So given a data set omega, think of that as a set of points in d-dimensional space, what we're going to do is we're going to look at the edge weights between a vertex u and v, and we're going to define them in the following way. Instead of having them be fixed, we're going to look at a random point x for my data set that went through the vertex u in its path down the tree, and a random point y that went through the vertex v on its path down the child vertex v on its path down the tree, and we'll look at their distance, an expectation over sampling point from u and a point from v. And that's going to be the distance of the edge weight. So now note this edge weight depends on the points. In particular, it doesn't make sense to ask about an edge weight for an edge that you didn't sample a point going down, because there's no point to sample from this expectation from. So the picture is you have this piece of space corresponding to the vertex u and a piece of space corresponding to the smaller vertex v, and you look at the expected distance between a point in the smaller one and a point in the bigger one. And that's your that expectation is your edge weight. Now, it's the same set of vertices, different edge weights. It turns out that this was actually enough to show a much better approximation factor. So what we showed in that paper was that if you just do this change, first of all, for the points in your data set, you get contraction deterministically. It's fairly easy to show this just by sort of a triangle inequality argument. So points never contract in distance. And moreover, the expected expansion is only a log omega factor larger than the original distance, where omega is the number of points you're embedding, the number of points that your tree depended on. So if you're thinking about things like streaming algorithms or distributed algorithms for computing EMD, you only have sort of two sets, A and B, and you want to like compute their distance in a stream. And so this tree embedding was enough to give a log S approximation for those problems. And so this paper was mostly about streaming because we were to get improved approximations using these data-dependent tree embeddings. But this result isn't good enough for nearest neighbor search. And the question is why? Well, I already sort of mentioned it a little bit earlier. But of course, we would like to use this for nearest neighbor search. But in that case, this set omega would have to be the union of all our sets in our data set. But there's n of them. And we think of n as being very large, maybe much larger than s. So then we would get a log ns approximation. And that's not ideal. There's another issue that this embedding is only defined for points that in the data set, and the query that you're coming may not be in the data set. So that's another issue. So we need to modify this so that we can get an embedding for all the points and still get a good approximation. We want this approximation of log s for all the points. So that's where I'm going to define this new thing that I'm going to call sample tree. This is sort of a hybrid data independent, data dependent embedding. And again, there's nothing too crazy going on here. What I want to do, we can't afford, this is the starting point of our algorithm. We can't afford to do this data dependent quadtree on all the points. So we want a log s approximation. Let's run it on poly s points if we can get a log omega approximation. So I'm just going to take my data set and I'm going to sample a random polynomial in s many sets from that data set, and I'll interpret them as the underlying vectors in d-dimensional space. And then I'm going to have the same exact tree as before, the same exact random partition of space, but I'm going to define the edge weights in a hybrid way so that now the edge weights are defined for all the tree. So I now have a bona fide embedding for the entire metric space. So you could kind of guess what the weights are going to be for any edge. If I sample the point that goes along that edge, well, let me set the weight to be the data dependent weight from the prior paper, the average distance between two sampled points. And if these orange points here, maybe these are the points I sampled, and the orange edges, the thick edges, those are the edges that would have data dependent weights because at least one point for my sample went down them. The other edges don't have any sample point, so I'm just going to set their weight fixed as a fixed value that's data independent. That was the same weight that was used in the Andoni, Indic, and Kraus-Gammer paper. So this is kind of a hybrid of the two in a very natural way. And now we want to ask, is this going to give us the result we want? Well, it's not, but it'll help us a little bit. So what is the distortion of this? How would we analyze this embedding? Well, first of all, let me let t sub omega be the sample tree metric. And it depends on omega, of course, so we're going to subset it by omega, subscript it by omega. So if I have 2 points that were in my sample, well, what is their distortion? Well, it's a log s distortion, just because their distance in the tree is exactly equal to the data-dependent distance that they would have had in the data-dependent quad tree. So they inherit this improved log s approximation. So that's great. But what about the rest of the points? Well, what about the points that are very far from omega? So if I had 2 points x and y that are like really far from the set of points I sampled, then you can imagine in the tree, all the edges they used to get from one to the other, they would all be data-independent edge weights. And so they might as well be getting the same guarantee that you would get from the data-independent edge weight paper, the log squared s. And of course, that's the case. So for points that are really far away from your sampled set, you're going to get a log squared S approximation. So already we know that this alone is not going to be good enough. But sort of the intuition is that this omega was a randomly sampled set of points from my data set. So on average, most points should hopefully be not too far from omega because it was a random sample. So hopefully not too many points are going to be only using the data independent edge weights. So what we could hope for is for the points that are close enough to my sample that they also get a good approximation. So in particular, for points x that are not in the sample, but that are close enough to some z in the sample, we could hope to extend the improved log s approximation that we were getting from those points in the sample to a neighborhood of that sample so that we get an improved approximation for a larger neighborhood. And this is sort of going to be the main technical challenge of getting an improved approximation here. We want to extend the result from a small sample to a neighborhood of the sample. So let me formalize what I mean by that. So what we want to prove is some statement that looks like this. If I have two sets A and B in my earth mover distance metric that are close to omega in some notion of closeness, then the earth mover distance under this tree metric, this modified tree metric between A and B, is a log s approximation of the original earth mover distance. This is the kind of statement we want. So first of all, what does it mean for a set A to be close to the sample set omega? Well, we've been talking about distance between sets. We've been talking about earth mover distance, but it turns out that earth mover distance probably isn't the right notion to use here. First of all, note that omega could be a much larger set than A. It's a large sample. And second of all, we don't need A to be close, every point in omega to be close to some point in A. We just need every point in A to be close to at least one point in omega to get near to the sample. And in fact, it doesn't even need to be a matching. So there's actually a distance that captures this. It's a relaxation of the earth mover distance. It's called the chamfer distance. So the chamfer distance is what you would get if you wrote down the LP for earth mover distance and you remove the matching constraint. It's a very simple metric. In fact, it's not a metric. It's not even symmetric, but it's a very simple object of study. It's used a lot in these NLP works. It just says for every point in A, find your nearest point in omega and sum up the distances. So it's basically looking at the average distance from point in A to its nearest point in omega. So wait, okay, yeah. So you can see here that like some of the points, the orange points don't even need to be matched to. And you can have 2 points in A matching to the same point in omega, and that's totally fine. So this is a relaxed notion of the earth mover distance metric, and it captures how, like, if you wanted to take every point in A and move it to its nearest point in omega, that's the chamfer distance. And that's a good way of thinking about it. Okay, so now we're going to use this to define the neighborhood we want to extend our approximation to. So we're going to try to first start by proving this following lemma, which I'm going to call the weak chamfer extension lemma. So this is going to be weak because it's not going to be strong enough for a result, but it'll give you an idea of sort of what's going on here. So what do I want to prove? I know that my distances aren't contracting, so I'm worried about the distance in the tree metric between two sets of points A and B. And what I'm going to prove is that their distance is at most log s times their original earth mover distance. That's my goal, plus an additional error term, which is log squared s times the chamfer distance from A and B to omega. You can think of that as the cost of moving A and B to the set omega. And this is going to be, this should be subscripted here with RD. So this is the chamfer distance in the original space. Okay, so there's a very simple proof of this. And it just uses facts we've already gone over and a bunch of triangle inequality. So what we're going to do is in the tree metric, we're going to take each of our points A and B. We're going to move them in the tree metric to their nearest point in omega and the sampled space. And then we're just going to match them up over the sample data dependent edges. So how much does it cost to move A and B to their nearest sample point? Well, that's the chamfer distance between A and B in the tree metric. But in the worst case, those are only using data independent edges, and we have the log squared s bound for that. So moving A and B in the tree to omega costs log squared n times their original chamfer distance. Next, once these 2 sets of points are at their nearest points in omega, let's say sigma is the function which maps A and B to their nearest points in omega, now we just want to do the earth mover distance to match up the points in omega A to the points in omega B. And that's just the earth mover distance in the tree between omega A and omega B. But these omegas, these were sampled points. So now they're only using the data dependent edge weights. So they get only a log s approximation. And so that's a log s times the earth mover distance between the omega A's and the omega B's. Sorry, the sigma A and the sigma B. But then we can just use triangle inequality again and say that the cost of matching 2 points up after they move to the sample is at most the cost of matching them up originally plus the cost of moving them back to where they were originally by triangle inequality. So again, this is another EMD plus the chamfer distance. And you could put these two things together and you get this bound up here. So we didn't really do anything tricky here. We just sort of applied the data independent bound and the data dependent bound and triangle inequality to show that the earth mover distance in the tree is the most log squared S chamfer plus the EMD. So what this is saying is that for points that are very close to the sample, let's say very close to the sample, closer to the sample than they are to each other, so like a log squared S closer to the sample than they are to each other, their earth mover distance in the tree is a good approximation. But for points whose chamfer distance to the sample is the same as their earth mover distance to each other, then the first term would dominate and we'd only get a log squared S approximation. So in the worst case, the distance from points to the sample is like roughly on the order of the EMD between these 2 points. You can imagine all points in your data set having the same earth mover distance to each other, and now you're not really saving anything by sampling points here. So this wouldn't be good enough. So what we really need to do is get a neighborhood extension where our approximation holds for points who are further away from the sample than they are to each other. A and B who are close to each other and a little bit further away from the sample. And that's what we're gonna prove in this so-called strong chamfer extension lemma. So this lemma is the main meat of the paper. And what it says is the following thing: the earth mover distance in the tree metric, we're able to show it's at most a log S factor larger than the original earth mover distance times this additional approximation factor. What is this approximation? Well, it's now much better than we had before. It's log of the ratio of how much larger the chamfer distance from A to B to the omega is divided by the EMD. So intuitively, what this is saying is that I have my point. I want to know what is this approximation into another point B? And so long as its distance to a random sample is only a polylog S factor larger than its distance to the point that you're trying to match it to, then this is saying that the approximation will only be a log S times factor larger than log S. Because the chamfer distance in this case will be like polylog S times larger than the earth mover distance, but this thing is sitting inside of a log. So this is why you get the tilde O of log S. So this is a much stronger result. This is saying that I can extend my guarantee to all the points in a chamfer neighborhood that's polylog S times larger than the scale I care about. And I don't really have much time to go into detail about this, but I'll give sort of a high level, and I think should be coherent, I hope, overview of like what's going on here. So when we proved this weak sort of chamfer neighborhood lemma, it was kind of a silly way of doing things. We moved the points A and B to the sample, and then we matched them in the sample. But if the sample is further than the points together, obviously you're paying triangle inequality. You're not going to get a good result here. So instead, what we're going to do is we're going to think about matching the points in A directly to the points in B. And the picture here is that A and B should be closer together in the tree than the point we sampled, because that's the case we sort of care about here. And the key sort of idea is that if you look at the point in the tree where A and B were supposed to match, what I mean by supposed to is that before then the weights in the tree are not larger than their distance should have been, then I don't actually care about splitting before those edges because the edge weights are small. What I care about is the point where I wanted them to split, and maybe where I wanted them to be together, and maybe they weren't together. But that's only an issue if I haven't yet gotten to a sample. Once I've gotten to a sample, now I inherit the data dependent weights, and I'm home free. I have the better approximation. So the only bad places are the places of the tree before I'm supposed to reach my close point. Maybe this is a good case, but maybe they split here. So before I was supposed to reach my close point, but before I haven't reached my sample yet. So these two edges here. And so I'm only going to overpay by some factor on those edges between the sample and the point B. And the point is that the number of such edges that I expect is proportional to the ratio between how much further, got excited. How much further chamfer distance is than the earth mover distance, how much further the sample is than the earth mover distance. And because these are geometrically increasing, every edge is like a factor of 2 here. So the thing goes into a log. So if the chamfer distance is a polylog times factor larger, there's only log S many edges that are these bad edges where we overpay. And so that's I've cheated by not giving a lot of information here, but hopefully I've convinced you that this is sort of how the proof goes. Okay, so this is sort of the main interesting thing that goes on. The last thing we have to do is sort of glue everything together. And I'll go through that quickly before everyone falls asleep. But one thing I'll just mention is that this chamfer A and B to omega, we can kind of just think of it as the chamfer from A to omega, because by triangle inequality, the cost of moving A and B to omega is the most of the EMD between A and B plus the moving just A to omega. So this property here, it sort of is just, it just depends on A in some sense, how far A is from the sample, not A and B. The reason that's interesting is now we can talk about sort of points that are close to a sample and points that are far from a sample. And so to define that, I'm gonna define this concept of a locally dense point. This is just a point that's close to the sample. So I'm gonna say that a set A is R locally dense if its chamfer distance to the set is less than R times some large polylog NS. And R is the scale that we're thinking about for LSH. And so now we just need sort of two simple lemmas to say that we can handle the far points, we can handle these close points with the sample tree thing, and the far points we can handle with the older embedding, if you remember from the sort of the outline we were going for. So the first thing I want to say is that if such a set is locally dense, if it's close to the sample, then this sample tree embedding gives a log S, log S approximation. And that, we already sort of just proved that before. If it's locally dense and this ratio chamfered to the EMD that we care about is less than log S, so we pay that extra log S factor. So we're in good shape. What about the points that are far from the sample? Well, if it's not locally dense, and here's where we're going to use, this is finally where we're going to use this idea of the second condition of data-dependent LSH, where remember the second condition was weaker. It only required us to split the far points away from with respect to a random draw of a far point from the data set, not all far points. And so how can we exploit this? Well, if A is far in chamfer from the sample, well, its earth mover distance is going to be even farther from a sample because, or earth mover distance is larger than chamfer. So that means that A is actually far, its earth mover distance is far from a random draw from my data set. So on average, over the data set, my point A is log 10s far from a random sample. So it's actually quite far from a random sample, and I'm only trying to distinguish like R from like log S times R. And so even though I have this old approximation, this log squared S approximation, even though it's not the ideal approximation I wanted, it can still distinguish between R and log 10R because it's a log squared S approximation. So it's good enough to tell the difference between a really far point and a close point. And because points that are far are really far on average, I only need this average case splitting from far points. And so putting these two things together gives us a log squared S approximation in both cases. And lastly, you have to know which one to output. And I won't really go through this because it's not really crucial. But essentially, the key final point is that when I get my query, I can actually figure out what case I'm in by just looking at the hash table. I can look at the first LSH, the data independent LSH, and look at the hash bucket. And if there's a lot of points in it, I'm like colliding with a lot of things. And I can conclude that I'm dense, that I'm like close to a random sample. And then I know, okay, I can use the sample tree algorithm. If the hash bucket is really small, well, then I can just use the first algorithm. And in fact, if you think about what you're trying to do in nearest neighbor search, if the hash bucket is small, I've already eliminated a lot of points from the data set. So I can kind of recurse and make progress. So the key idea here is you can actually tell what case you're in by looking at the data at the bucket that you created in the hash table. And that's how you glue them together. And that sort of completes the plan that I hope to tell you about by putting all these things together. So let me, before I ask, let me just mention two open problems. I have a couple of minutes. So this sort of thing came from a sequence of works where we've been trying to understand how to better get a handle on this complex metric EMD, because a lot of the common techniques don't really work. The best thing we can do is try to embed it into a simpler metric and get a handle on that cost of that embedding. But there, and we've been able to do that by developing embedding techniques that are more and more applicable to different models, like streaming and property testing and distributed algorithms, now nearest neighbor search. And so one issue is that like some of these, sort of the grand hope is that you'd have a very, very oblivious sketch of this algorithm, because sketching is one of the most versatile models. And let me now say really briefly what that is if you haven't heard of it. So the sketching model would be Alice and Bob. Alice has the set A and Bob has the set B, and they want to compute the EMD. and they want to minimize the number of computation. Look at communication complexity problem. So if you had a data-independent LSH, this would give you sketching, because they could just, Alice and Bob could take the LSH, they could hash it, and they could share the ID of the hash bucket. If they match, they know it's close. If it's not, it's not. So this is one point where data-dependent LSH is not as strong as data-independent. Because for Alice and Bob to construct the data-dependent LSH, they would have to know each other's input. And of course, that's the whole problem. So even though we've now got a better approximation for sketching, and the prior paper gave a better we have a better approximation for nearest neighbor search. This prior paper got a better approximation for streaming. We still don't know how to get a log S approximation for sketching algorithms. The best we know right now is log squared S. So there still seems to be even to get a log S approximation, which we know feels like possible for EMD, there's still some models where we don't know how to do it. And lastly, you could hope for even better. You could hope for all these models, can you get a constant approximation? It seems like, and I sort of believe strongly that you can't, but it's really hard to prove lower bounds on a lot of these models. In this paper, we were actually able to rule out a large class of localities of hashing, where we were able to show that you can't get a constant factor LSH unless maybe it allows close points to collide with very small probability, which is rare and doesn't really usually happen in LSH, but we couldn't rule out that case. So, you know, it seems unlikely, and of course you could solve nearest neighbor search with some other technique, but people don't usually do that. So it seems unlikely, well, not in theory, sorry. As a practitioner, I have to say that we solve nearest neighbor search differently, but it seems difficult to get a constant approximation, but you know, we really don't have a ton of techniques to show that. So hopefully we'll get some progress in the next couple of years. So that's all I want to tell you about. Thank you so much.
Say you have a set of spheres, and each time you carry a point and you ask the sphere.
So you have a set of spheres.
Yeah.
So your data set consists of spheres in some high dimensional space,
Yeah.
and you get a single point.
Yeah, the query.
The single point, and you want to find the nearest sphere. This is kind of like the Hausdorff distance. Well, I guess it's just the nearest distance to a set of objects. So this is similar to just like, this was sort of reduced to normal nearest neighbor search, right? Because you could take the set of the sphere and sort of make a, you know, a net over it. But I guess this would be exponentially sized if you're in high dimensional space. That's an interesting point. I think there may have been papers on this in low dimensional geometry, but I don't know of any works in like if you think about high dimensional spheres, the natural thing to do doesn't work because you would have exponentially many points. That's a good question. I don't know of works that do that.
Like any data structure, like classic data structure works with it?
Well, if you took each sphere and expanded into 2 to the dimension many points in the net, then you could use the classic data structures. But I don't know of an algorithm that would work off the shelf. I mean, because the thing is like, what LSH, they're space partitions. And so you're partitioning space randomly, and then points end up in a bucket. But your sphere could cross multiple LSH buckets. Yeah, and you would have maybe if you had some bound on the diameter of the spheres that you cared about, like if you wanted to tell whether there was a sphere within distance r versus c times r, and if all the spheres had diameter, let's say less than r times 1/log s, so they were smaller than the radius you cared about, then you could actually hope that most of them are fully contained inside of a hash bucket, because there's sort of this like log s gap that you need in these partitions. If you didn't have that, like if it was roughly on the order, it could intersect exponentially many hash buckets. So the natural thing to do, which would be to look at all the hash buckets where that would give you an exponential blow up. But that's a really interesting question. Someone should think about that. Go ahead. Which distance, Earth mover? It's easily computable.
Yeah.
Well, Euclidean space is not one of them. There's a classic paper of Tarjan in the 1950s that says even for the line, like the greedy algorithm for EMD can get like a root worse than a root n approximation. So like even for the line, it's not the case. You might ask, is the line a tree metric? There's a caveat there. But I don't know. There's not like a good classification, I think, of like sort of in my mind, either if the greedy algorithm works for the space, it's an easy space. If the greedy algorithm doesn't work, there's probably not another good algorithm. And sort of an open problem that I've been saying a lot, and it's sort of an informal open problem is there like a good local algorithm for EMD? Is there an algorithm that doesn't use a lot of, like, so how does the Hungarian algorithm work? It does like augmenting paths, and it requires information of the entire data set. So that's why it's so complicated. You can't just each point in the data set locally figure out which point you want to match to. If there was a good local algorithm that got, like, say, a constant approximation, then you could hope to get, like, all of a sudden distributed algorithms and like fast streaming algorithms for Earth mover distance with a constant approximation. But we don't know of them. So there's very few spaces